provided an immense boost up and new dimensions to material research and nanotechnology. However, like other 2D material, graphene research also need some amendment and upgradation in light of recent scientific output. One more thing, graphene has the best electrical conductivity of any material. 2D material such as graphene are the best hot topic today's now. My dear friends, in today's presentation, I will cover the following topic. First topic is what is graphene. Second one topic is the different source of graphene. Next is creation and isolation of graphene. Next, graphene transistor. Next, comparison between graphene and silicon material. Next, what are the graphene field effect transistor designed? Different software used for the 2D material. Next one, what are the benefit of graphene transistor? Next, how are graphene field effect transistors produced? Next, fabrication advantages of the graphene. Next, current graphene transistor production challenges, and the most important, literature survey of the graphene transistor. My dear friends, graphene is the thinnest material known to man at 1 atom thick and also incredibly strong, about 200 times stronger than steel. On top of that, graphene is an excellent conductor of heat and electricity and has interesting light absorption abilities. Graphene is a 1 atom thick layer of carbon atom arranged in a hexagonal lattice. It is the building block of graphite. Graphite exhibits a multi-layered structure. Each single layer of graphite is composed of hexagonal lattice in which the individual carbon atoms are chemically linked together by a strong covalent bond. The individual carbon atoms are separated by a distance as low as 0.142 nanometer in the mono-layered hexagonal lattice. Graphite is a commonly found mineral and is composed of many layers of graphene. Graphene is a commonly found mineral and is composed of many layers of graphene. The structure, makeup of both graphene and graphite and their fabrication method and technology are slightly different. Graphite mineral. Graphite is one of the 3 naturally occurring allotropes of carbon and occurs naturally in metamorphic rock in different parts of the globe, including South America, Asia, and some part of the North America. The mineral is formed as a result of reduction of sedimentary carbon compound during metamorphism. The chemical bonds in the graphite are similar in strength to those found in the diamond. However, the lattice structure of carbon atom contribute to the difference in hardness of these two compounds. Graphite contains 2-dimensional lattice bond, while diamond contains 3-dimensional lattice bonds. The carbon atom within each layer of graphite contains weaker intermolecular bond. This allows the layer to slide across each other, making graphite a soft and malleable material. Next is the properties of a graphite mineral. Various studies have demonstrated that the graphite is an excellent mineral with several unique properties. The first property is it conducts heat and electricity and retains the highest natural strength and stiffness even in the high temperature exceeding 3600 degrees C. Second property, the material is self-lubricating and is also resistant to chemicals. Although there are different forms of carbon, graphite is highly stable under standard conditions. Depending upon its form, graphite is utilized for a wide range of applications. Although there are different applications of graphite mineral, but in this slide I have covered only 2 properties of graphite mineral. Next is the graphene bundle material. Graphene has unique properties that exceed those of graphite. Although graphite is often used to reinforce steel, it cannot be utilized as a structure material on its own because of its shear planes. We cannot use graphite as a structure material or device material. In contrast, graphene is the strongest material ever found. It is more than 40 times stronger than the diamond and more than 300 times stronger than A36 structure steel. Since graphite has a planar structure, its electronic, acoustic, and thermal properties are highly anisotropic. Anisotropic is the property of the substance to exhibit variation in physical property along different molecular axes. This leads to different physical and chemical properties in single crystal along the different axes. This means phonons pass much more easily along the planes than they do when trying to pass by the planes. However, graphene has very high electron mobility, and like graphite is a good electrical conductor due to their occurrence of a free pi electrons for each carbon atom. However, graphene has much higher electrical conductivity than graphite due to the occurrence of quasi-particles, which are electrons that function as if they have no mass and can travel along long distance without scattering. Graphene has a number of advantages than graphite, such as electrical conductivity due to the occurrence of quasi-particles. Creation or isolation of graphene. Scientists use a number of techniques to produce graphene. Mechanical exfoliation, also known as adhesive tape technique, is one of the effective ways of creating single layer and few layer graphene. However, various researcher institutions worldwide are trying to find the most efficient way of creating high quality and cost effective graphene on a large scale. Chemical vapor deposition is the most suitable technique for producing monolayer or few layer graphene. This technique is capable of extracting carbon atom from a carbon rich source by reduction. However, a major drawback in this technique is the difficulty in locating a suitable substrate to grow graphene layer on, as well as the complexity in removing the graphene layer from the substrate without altering or damaging the graphene's atomic structure. Other techniques for growing graphene are sonicitation. Sonicitation is the act of applying sound energy to the various carbon component for various purposes, such as an extraction of multiple components from them. Another is thermoengineering, carbon dioxide reduction, cutting open carbon nanotubes, and graphite oxidation reduction. There are different techniques to produce graphene. The later technique, graphite oxide reduction, is using of heat to reduce graphite oxide to graphene, has recently attracted significant attention in the area of reduced cost of production. However, the quality of the graphene produced presently does not meet the theoretical potential of the material and will take some more time to become perfect. Next method to produce graphene is a graphenia. Graphenia is a leading graphene producer for industry and research needs. Graphenia has developed a leading synthesis and transfer process to obtain high uniformity monolayer graphene film on any substrate. There are different advantages of graphene are given below. First one is the space elevator. Because of lightweight and strongness of graphene, it can be used in the space elevator. Second one is the drinking ocean water. Membranes made from graphene can allow water to pass through but filter out sea salt. In fact, one of the group of the researchers found that graphene is so effective at filtering seawater. Next is the super strong body armor in military. Two atomic layers of graphene make a stronger bond. Scientists try to penetrate with them with a diamond tip, but it cannot possible. So that graphene can be used as body armor in military. Next is the healthcare. Graphene is important to improve application in medicine, cancer therapies, disease diagnostic tool, tissue engineering, implants, DNA squeezing, biomarker, transfer of genetic material, as well as in the combined field of biomedical imaging and neuroscience. Next advantage is recharging gadget. Graphene offers higher electrical conductivity than lithium-ion batteries. This allows for faster charging cells that are able to deliver very high current as well. This is particularly useful for car batteries, for example, or fast device-to-device charging. Flexible and strong smartphone display. Different researchers from the University of Sussex in England found a solution to hard smartphone screens by combining silver nanowire with graphene. A 1 atom thick material has a 200 times stronger than steel, more conductive than copper, and as flexible as rubber. Is used in flexible and stronger smartphone displays. Next advantage is running shoes for new generation. Collaborating with graphene expert at the University of Manchester, the brand has been able to infuse the wonder material into rubber. They have developed rubber outsole for running and fitness shoes that is testing have outlasted 1000 miles and are scientifically proven to be 50% harder wearing. Next advantage is solar cell. Graphene has shown greater potential in transparent electrode as a replacement for indium tin oxide in polymer-based solar cells. The graphene in the electrode becomes an organic-inorganic hybrid material, and after it undergoes coating, layering and reduction and temperature annealing, it is best suited for the solar cell. Next is the graphene transistor. Graphene transistor is a nanoscale structure dependent on graphene, a part of the graphite with electronic properties far better than those of the silicon. It is a single electron device, which implies that a single electron, one electron, goes through it at any one time. Graphene is a one atom layer of carbon atom in 2D hexagonal lattice. Properties of the graphene transistor consist of stronger electric field and higher carrier mobility. This is the most important advantages of graphene transistor. Momentum changes narrow ribbons of various length, and it occurs due to the tunable band gap of the graphene. It lies between 0 and 0.25 electron volt. Operate at room temperature. Dimensions of one atom is 10 times of silicon atom wide. Highly sensitivity. It can produce high sensitivity device. It can be used in very low voltage application. This is the most important advantages of the graphene, so that it can be used in the nanoscale device. Next is the comparison between graphene and the silicon material. Graphene based device has quick processor in microchip innovation as compared to silicon as their semiconductor material. Graphene has a high carrier mobility because of electron can move easily through graphene without any resistance. Electron can move through graphene at a speed of 10 to 1000 times greater than silicon material. Furthermore, unlike silicon, graphene's property actually improve as the device becomes smaller. That capacity, coupled with the ability to operate at room temperature, would allow more miniaturization of the device would be possible. It allows more components to be placed on one integrated IC chip. Recently, researchers have proposed graphene as a base material for transistor. Because of the atomic thickness, the graphene base is almost transparent to electron transport, leading to a negligible base transit time. At the same time, the remarkably high carrier mobility of the graphene will benefit the base resistance compared with a thin bulk material. Graphene-based transistors generally use a tunnel emitter that emits an electron through an insulator. However, the emitter potential barrier height seriously limits the cutoff frequency of the device. With further engineering, the vertical semiconductor graphene semiconductor transistor is promising for high-speed application in future 3D monolithic integration because of the advantages of atomic thickness and high carrier mobility of the graphene. Next is what are the graphene field effect transistors. Graphene has been revolutionizing electronics since October 2004 when Andrew Zam and Kostya Novoslia first determined how to remove a single layer of carbon lattice from the graphite. Second one, the production and the research of today's graphene field effect transistor would now have been possible without the past 2 decades of the research and offer many benefits over traditional bipolar junction field effect transistor. This is all thanks to the inherent qualities and properties of graphene, which means graphene field effect transistor can be used to good effect in a range of technologies, including biological and chemical sensor. Next is the structure of graphene field effect transistor. Graphene field effect transistor take the typical FET device and insert a graphene channel 10 of micron in size between the source and the drain. Being graphene, a lattice of carbon atom that is only one atom thick, the channel in the graphene field effect transistors have recorded high sensitivity, which can be exploited on a wide variety of applications such as photosensing, magnetic sensing, and biosensing. While the carbon in graphene typically does not react or bind with the most materials, bioreceptors such as amino acid, antibodies, or enzymes can be added through adsorption or a wrinkle molecule attached to the channel surface. Molecules can then attach to these sites through covalent bonding, electrostatic forces or van der Waals forces, imparting an electronic transfer through the entire path of the device. Graphene FET can also be used as a gas detector. Next, how to build a graphene field effect transistor. You can build graphene field effect transistor using the quantum ATK builder. We shall consider a nanoscale graphene nanoribbon transistor with a metallic gate separated from the ribbon by a dielectric. If we want to simulate its property by electroanalysis, I would strongly recommend use COMSOL multi-physics device. Next, what are the benefits of graphene transistors? The most of the transistor sensors are three-dimensional. Electric charge changes at the surface of the channel do not always penetrate deeper into the device. This can dramatically limit the response sensitivity of the device. On the other hand, as the graphene in a graphene field effect transistor is only one carbon atom thick, the entire channel is now on the surface, which directly exposes the channel to any molecule present in the nearby environment, so that it is best suited for the sensor device. The micrometer sized sensor fabricated from the graphene were capable of detecting individual gas molecules attaching to or detaching from the surface. Fewer molecular defects in graphene. Semiconductors such as silicon are incompetent when created to be as automatically thin as graphene. This is because surface defects such as dangling bonds tend to lead at this thickness, which lower the overall sensitivity of the device. In case of silicon material, such bonds form additional defects in the sensor's semiconductor channel and make non-specific binding possible. This will giving rise to the false positive to the device. Third one, this is unlike graphene, which can be formed in a single layer with a high degree of correctness and precision. Furthermore, a two-dimensional material such as graphene produced efficiently will have much less dangling surface bonds. Another advantage of graphene is the superior conductivity. Graphene field effect transistors also have a higher carrier mobility than traditional field effect transistors, often reaching level greater than the 1 lakh centimeter square per volt per second for HBN encapsulated single layer CVD graphene. These devices also have a residual charge density as the order of 5 into 10 to power 11 per centimeter square. Now the most important part is how are graphene field effect transistors produced. Graphene field effect transistors are generally fabricated on a Si-SiO2 substrate with metal contacts. The graphene itself is deposited on the wafer through chemical vapor deposition. The first step to the chemical vapor deposition is the decomposition of carbon source at high temperature. The carbon atoms are then laid down on the deposition substrate where eventually the typical hexagonal lattice we know of as graphene form. In both stages of the production process, the careful use of a catalyst such as copper, iron or nickel is required to lower the effective temperature required from over 2500 degrees C to a more manageable at 100 degrees C. The graphene layer is transferred from the deposition substrate and overlaid onto a wafer which is typically made of silicon. Next, metal electrodes are deposited on the graphene lithographically, while further lithography is used to shape the graphene channels themselves into the size of the shape of the device that is desired. This is the structure of the graphene field effect transistor. You can see on the presentation. This is the graphene layer deposited on the SiO2 surface. This is the silicon material. This is the SiO2. These are the metal contact for drain and the source. Next is the fabrication advantages of using graphene, as well as the sensitivity benefits mentioned previously of the graphene field effect transistor when compared to the bulk semiconductor transistor materials. Graphene field effect transistor have a number of distinct fabrication advantages over other devices created using one-dimensional material such as carbon nanotubes or nanowires. While these materials are highly conductive like graphene, they as yet cannot be manufactured with the same precision. During the production of one-dimensional objects such as nanotubes, the number and the orientation of these objects will vary across a random distribution. The non-uniformity means an array of high yield yet uniform response device is impossible to fabricate using current technology. This randomness is further highlighted by varying dimensions of thickness and width within the one-dimensional object themselves. On the other hand, the use of photolithographic fabrication technique can deposit and shape a two-dimensional layer of carbon atom with high precision in the device. Current graphene transistor production challenges. One of the difficulty in creating graphene sensor of high sensitivity is mass producing graphene without defect or impurity is not possible. Fortunately, steps have been taken toward high quality CVD growth, chemical vapor deposition growth, and transfer such that the graphene is free from metallic contaminants, cracks, holes, folds, or residues. Work is now being done to move the production of graphene field effect transistor sensors from the lab to industry, although scalability problem may still remain an issue depending on the technique used. The researcher from the University of Pennsylvania Department of Physics and Astronomy uncovering a way to mass produce level free graphene field effect transistor DNA biosensor through a CVD fabrication process that offer greater than 96% yield. Some more challenges in graphene field effect transistor fabrication. We don't talk much about the graphene these days. After a furious round of excitement and research half a decade ago, the topic was largely cooled off. Part of the reason why is because it proved incredibly difficult to manufacture in quantities that were useful. It is difficult to produce high quality graphene at mass production level. Second one, they note that in the case of graphene contaminated with metals, the metallic particles would interfere with the performance of the graphene electrode in any battery. The final conclusion is that there is almost no high quality graphene as defined by the ISO in the market yet. The lack of properly characterized high quality material has been stalling the development of application that depends fundamentally on graphene, such as advanced coating and composite high performance battery and the supercapacitors, etc. The purpose of the literature survey is to provide the foundation knowledge of the device. Literature survey. A literature survey is very important. The purpose of literature survey is to provide the foundation knowledge of the device. A literature review is a comprehensive summary of previous research on a topic. While attempting to understand the electronic properties of the 3D graphite, a great researcher, Valence in 1947, explored the theory of graphite. During this period, after one decade, one another great researcher, McCullough in 1957, proposed the bone structure, which is called as Slunjiki-Vesey-McCullough band (SWM) structure. The model experimental are well explained by number of researchers from 1958 to 1977. But SWM structure are not able to explain interaction between graphene planes. The first synthesis and characterization of the monolayer graphene was achieved by 2004 by Costea, and this group also received the Nobel Prize in Physics in 2010 for this. The other interesting aspects of graphene problem is the massless chiral drag formation or its low energy excitation. One more thing, graphene is a gapless semiconductor. The speed of electron in graphene is a constant, just as the speed of the photon is a constant c. With the difference is that graphene direct fermions move with a speed of 300 times slower than the speed of light. MC Lamy in 2007 proposed a top-gated field effect transistor manufactured from monolayer graphene is investigated. In 2013, Merrick proposed two-dimensional atomic sheet of graphene represent a new class of nanoscale material with potential application in electronics. However, intrinsic characterization of graphene device has been problematic due to impurity and disorder in the surrounding dielectric graphene and dielectric interface. In this paper, recent advancement in fabricating graphene heterostructures by introducing crystalline hexagonal boron nitride layering with graphene. Its insulating isomorphs have led to an order of magnitude improvement in graphene device quality. In 2013, Sebastian proposed a new scalable electrical compact model for the graphene field effect transistor device. This large signal model has been implemented in Verilog A code and can be used for the simulation in standard circuit design environment such as Cadence or ADS. In 2015, Atul Kumar and Rohit Sharma proposed an analytical model for the computation of equivalent capacitance in top contact and side contact multilayer graphene nanoribbon interconnects is introduced. Based on this model, it is seen that the interlayer capacitance is a leading factor that seriously reduces the performance of graphene interconnects. The proposed model is checked with simulation data obtained using synopses that show good accuracy. In 2016, again Atul and Rohit Sharma investigated the significance of lithium intercalenes in multilayer graphene nanoribbon interconnects for getting better performance than conventional copper on-chip interconnects. This paper proposed the first-time investigation analysis of a lithium intercalated multilayer graphene nanoribbon. In 2017, Chandward explored that the graphene is the thinnest material known to man at 1 atom thick and also incredibly strong, about 200 times stronger than the steel. On top of that, graphene is an excellent conductor of heat and electricity and has interesting light absorption abilities of the graphene. Graphene can also be added to the metal polymers, and the ceramics to create composites that are conductive and resistant to heat and pressure so that it can be used for the pressure sensor and the GAN sensor. In 2018, Kunal Biswas analyzed the outcomes of silicens and graphene at nanometer scale to understand the potential interaction mechanism between the two known nanosheets, which would be help in fabrication of the silicon graphene based optoelectronic device. In 2020, Nita Singh proposed a graphene field effect transistor based retina with substrate integrated waveguide broadband approach for RF signal harvesting application. The proposed structure of integrated retina consists of a graphene field effect transistor rectifier and substrate integrated waveguide antenna operating in the range of 29 to 46 GHz. The peak gain of the SIW antenna observed is 8.12 dBi. And the last one in 2020, Thomas John simulated a novel graphene nanoribbon based field effect transistor and used it to detect propane and butane gases. These are flammable household industrial gases that must be detected to avoid serious accident. Nanoscale simulation of FET-based sensor have been done in quantumized atomistic toolkit (ATK). ATK is commercially available nanoscale semiconductor device simulator that is used to model a large variety of nanoscale devices. This is end of the literature survey of the graphene. I know it is boring, but you must know if you start to work on the graphene field effect transistor or 2D materials. Most of the students called me and asked that can we use graphene in Silvaco TK tool and how can I simulate 2D material based device in Silvaco TK? The answer is it will depend upon case to case. For example, if you are using graphene as a contact in solar cell, you can define it as an ordinary contact and then specify its properties like reflectance. If you are using 2D material as a channel material, some define it as a resin with a very small thickness and then specify its characteristics including band gap, effective mass, mobility, density of state. But I have a suggestion for you. If you are using the graphene in a Silvaco TK tool, you does not get trustable outcomes since Silvaco does not cover loads of quantum calculations, but you can check it in its user manual which you can find in the website. On the other hand, if you just want to investigate transport properties of a 2D material, you might be able to code by yourself and use the properties extracted by the available DFT codes. Quantum Espresso, WASP, SISTA. Next one. If you want to simulate its property by electroanalysis, I would strongly recommend to use COMSOL multiphysics software. Next, so how to define graphene material in Silvaco Atlas TK tool? You can define graphene as a user.material as flowing in the reason statement. Reason number with their positional parameter, user.material graphene. And in the material statement, for example, if you need graphene as semiconductor, material, material graphene, electron band gap, affinity, mobility of electron, mobility of hole, permittivity, density of state for conduction band as well as valence band, TAUP and TAUN, index.file, graphene.nk, user.group semiconductor, user.default, for example, ITU. You need to create a file called the example graphene.nk in your working directory, which include the refractive index n and the excitation coefficient k. You can get this file by click on the link given in the description, that is file xenon.nk. An example for explaining. The number above 40 is the number of lines. The first column is the wavelength. The second column is the refractive index n of the material, that is graphene in your case. The third column is the excitation coefficient K of the material. Both indexes N and K are according to the wavelength. However, I think this really does not give trustable outcomes since Silvaco does not cover loads of quantum calculation.